Yeah, our next speaker is Mr. Ravi Asrani from India. He's on the title Derivative of Rational Functions. Ravi Asrani is a qualified and experienced math teacher who has been studying, researching, and teaching mathematics since 1998. He is founder of Omni Academy for Vedic Maths at Indore. Ravi Asrani has published research papers and has conducted many Vedic mathematics workshops in schools and colleges. He's trainer and faculty for Certificate and Diploma courses of Vedic Maths from Atal, Bihari, Vajpayee University, Bhopal. Presently, he is pursuing Ph.D. in Vedic Maths from Yoga-Samskrutham University, Florida, U.S.A.
Raviji, you can share your screen, or do you want me to share your presentation, or you can share your screen? I've made you the.
I'm sharing my presentation. Thank you for my introduction. Am I audible?
Yes, you are. Thank you.
Namaste to everyone present in this session. Just a minute. Is the screen visible?
Just a minute. Yes, Raviji. Thank you.
It's a pleasure for me to present applications of Vedic mathematics in calculus.
Okay.
Yes, sir.
Just give me 1 minute to get it. It's still showing, Raviji, it's still showing the PPT mode and not the screen mode.
Okay.
Maybe you can stop sharing and then go on to that screen. So stop sharing and go on to that, then share again with that screen, with the presentation mode screen, yeah? Uh, no, it's still showing the PPT mode, Raviji. When you share, instead of sharing the window, if you can share the screen.
So if he clicks on from beginning,
try from beginning and see what happens.
next left button,
Yeah,
left one.
Yeah,
from
but
beginning.
what's happening, Srinivasa? No, Srinivasa, what's happening is it's still showing the PPT. He's not. Raviji, click. When you share, instead of sharing that window, share the screen. That will help.
Okay.
Yeah, got it. Thank you so much. This works perfect. Thank you, Raviji.
Thank you. As we all know, that calculus is one of the most important branches of mathematics, which deals with continuous change. There are many applications of calculus in engineering, in science and social science. There are two major branches of calculus, differential calculus and integral calculus. Differential calculus deals with instantaneous rate of change and slopes of curve. Today we will see how differentiation of rational functions can be done in smarter and faster way by using Vedic Maths Sutra Urdhva Tiryak Vyam. The literal meaning of this sutra Urdhva Tiryak Vyam is vertical and crosswise. It is general method of multiplication. General method of multiplication is also based on this sutra. As the name suggests, this method of multiplication consists of steps including vertical and crosswise multiplication and giving the answer in one straight line. This method can be carried out from left to right or from right to left. The steps involved can be understood with the help of this ray diagram. Now come to rational function. Rational function is simply ratio of polynomials in the form u upon v. Polynomial is an algebraic expression which contains one or more term, and in each term power of variable should be non-negative integer. In present mathematics system, the derivative of rational function is generally obtained by using quotient rule. If u and v are differentiable functions in x such that v is not equal to 0, then d by dx of u upon v is given by denominator d by dx of numerator minus numerator d by dx of denominator over denominator square. These formula are also required for the differentiation of rational functions along with quotient formula. Prerequisite is to know these formula. ddx of x to the power n is nx to the power n minus 1. d by dx of constant is 0. d by dx of k times fx is k times d by dx of fx. d by dx of sum of functions is equal to sum of derivatives of functions. Here we have simple rational function, that is ratio of two linear binomials to differentiate. Y equal to ax plus b over cx plus d. Applying quotient rule, denominator differentiation of numerator minus numerator differentiation of denominator over denominator square. Formula is very easy to use. Prerequisite is just to know differentiation of polynomials, as d by dx of ax plus b is a and d by dx of cx plus d is c. So we have got this answer, but simplification is lengthy and time consuming and also prone to error. On simplification, we got this answer, AD minus BC over CX plus D whole square. Now I illustrate differentiation of same problem, y equal to ax plus b upon cx plus d by Vedic Maths method. Vedic Maths method of differentiation of ratio of polynomials resembles with vertical and crosswise product, which we studied as general method of multiplication based on Sutra Urdhva Tiryakvyam. But here we will use only crosswise rule. We will not use vertical multiplication. The method is, first of all, construct a rectangular array such that coefficients of x to the power 0 and x to the power 1 are to be written in the column first and second column respectively, below x to the power 0 and x to the power 1. Proceed from right to left and apply crosswise rule of multiplication. A times D minus B times C. Put a minus sign in between. And multiply this difference of partial products with difference of exponents. 1 minus 0. And denominator of the answer is square of the given denominator. So answer is AD minus BC upon CX plus D whole square. We take one more example to better understand the process. Here we have a ratio of two trinomials, quadratic trinomials to differentiate. Again, if we apply quotient rule, denominator as it is, first we are using a method of present mathematics system, modern math system. Denominator as it is into differentiation of numerator minus numerator differentiation of denominator over denominator square. Formula is easy to use, but simplification is tedious job and prone to error. As you see, numerator containing 12 terms to simplify. On simplification, we get answer 3x square plus 12x plus 3 over 3 plus 2x plus x square. Now I illustrate differentiation of same function by Vedic Maths method. First of all, we construct rectangular array such that coefficients of x to the power 0, x to the power 1 and x to the power 2 are to be written in the first, second and third column beneath x to the power 0, x to the power 1, x to the power 2. First we apply crosswise rule in first two columns. That is 5 times 3 minus 6 times 2. 15 minus 12. And this difference of partial products is to be multiplied by difference of exponents, that is 1 minus 0. So this is the first term of answer. First term of numerator of answer, constant term 3. For second term, we apply crosswise rule in first and third column. That is 4 times 3 minus 6 times 1. We put a minus sign in between. And difference of this partial products 12 minus 6 is to be multiplied by difference of exponents 2 minus 0. 2 minus 0. So this is second term, 12. It will be coefficient of x. And for the third term, we simply we apply crosswise rule in second and third column. 4 times 2 minus 5 times 1. That is 8 minus 5 is 3. And difference of exponents is 2 minus 1. This is coefficient of x square. So 3x square is the third term. So this will be the answer. 3x square plus 12x plus 3 over 3 plus 2x plus x square whole square. If the same question is done by modern maths method, then how much time it will take? Think on it. Because we have to simplify 12 terms of the numerator. It is easy to use quotient formula, but simplification is time consuming. There is one more example, a little complex example. A ratio of two polynomials having 4 terms. We are using Vedic method only. Because if we use modern maths method for this question, then a numerator will contain about 24 terms to simplify. For the first term of the answer, we use crosswise rule. Again, we construct a rectangular array such that coefficients of x to the power 0, x to the power 1, x to the power 2, and x to the power 3 are to be written in respective columns. First, we apply crosswise multiplication rule in first two columns. So 5 minus 8 multiplied by difference of exponents 1 minus 0. This will be first term. For second term, we apply crosswise rule in first and third column. 1 minus 12 multiplied by difference of exponents 2 minus 0. This is coefficient of x. So minus 22x is the second term, sorry. For the third term, we apply crosswise rule to first and fourth column. 2 times 1. We proceed from right to left. 2 times 1 minus 4 times 4. Multiplied by difference of exponents 3 minus 0. Also, we apply crosswise rule in second and third column. 1 times 2 minus 5 times 3. Multiplied by difference of exponents 2 minus 1. This is coefficient of x square. So minus 55x square will be third term. For fourth term, we apply crosswise rule in second and fourth column. 2 times 2 minus 5 times 4. Multiplied by difference of exponents 3 minus 1. This is coefficient of x cube. This will be fourth term, minus 32x cube. And for last term, we apply crosswise rule in last two columns. 2 times 3 minus 4 times 1 multiplied by difference of exponents 3 minus 2. This is coefficient of x to the power 4. This will be the answer. If the same problem is done by modern maths method, then numerator will contain about 24 terms to simplify. Then think on it how much time it will take. So Vedic maths method are very easy to use, very easy and very fast. This is one more example. For we simplify and we are writing the problem in tabular format as a standard format, coefficients of x to the power 0, x to the power 1, x to the power 2. Apply crosswise rule in first two columns. 5 times minus 8 minus 6 times 7. This will be the first term, minus 40 minus 42. For second term, we apply crosswise rule in first and third column. 1 times minus 8 minus 6 times 0. That is minus 8 minus 0 multiplied by difference of exponents 2 minus 0. This is coefficient of x, second term. And for the last term, we apply crosswise rule in last two columns. 1 times 7 minus 5 times 0. 7 minus 0 multiplied by difference of exponents 2 minus 1. That is 1. So 7x square will be the last term. So this will be the answer, minus 82 minus 16x plus 7x square over 7x minus 8 whole square. We can solve these problems mentally without writing these problems in standard format or without constructing a rectangular array. We arrange polynomials in increasing powers of x. Then we applied crosswise rule in first two columns, that is 6 times minus 15 minus 2 times 3 to get first term. Then we apply crosswise rule in first and third column, 1 times minus 15 minus 1 times 3 multiplied by 2 minus 1, 2 minus 0. So minus 36x will be the second term. For the last term, we apply crosswise rule in last two columns. That is 1 times 2 minus 6 times 1 multiplied by difference of exponents 2 minus 1. 6 minus 2, 2 minus 6 is minus 4. So minus 4x square. So this will be our answer. Minus 96 minus 36x minus 4x square over minus 15 plus 2x plus x square. So my presentation comes to an end. These are some practice questions. So I conclude by saying that these methods are very easy to learn, fast to use, and less prone to error. And if these methods are included in curriculum, then students of 6th, 7th grade can also learn this calculus part, which we are presently studying in 11th and 12th standard. Here we have used only crosswise rule. We have not used vertical multiplication. The reason is in vertical multiplication, terms cancel out because the difference of powers is 0. And in usual vertical crosswise method, it is some different way to apply vertical and crosswise rule. Also, Tirthi, founder of Vedic mathematics, tells us that Vedic mathematics did not advocate any fixed sequence for expanding the subject. So I have presented very little of so much available. Thank you.
Thank you, Ravi ji. James, do you want to say a few words?
Thank you, Ravi. That's beautiful. Really, really lovely. I've got a couple of questions. First of all, why did you set out the polynomials in ascending powers of x rather than descending powers of x? presumably it can be done with setting it up the other way.
Yes, there is no need to arrange powers in ascending order. We can arrange as polynomials are given as in standard form when powers are arranged in decreasing orders generally. We can do the same multiplication from left to right as we are doing from right to left.
And the cross subtraction then would go the other way.
Yes,
Yeah.
yes, yes. The method will be slightly different only.
And if the degree of the numerator is greater than the degree of the denominator, what do you do? Do you add in zero
Yes,
terms?
yes, yes. We can add zero terms.
Right.
This can be done by the same method.
It's great.
Thank you so much, Dennis.
It's really, really good. Thank you.
Thank you, Raviji, and thank you so much.
Thank you.
And